Okay, so let's move to lecture 2. The driving forces for mass transport. So in order to, in this lecture, we'll put more efforts on the mass transport process and how to describe the mass transport in your materials. People will usually use the atomic flux. So it's how many atoms passing through per unit area per unit time. And based on Fick's first law, you know it's equals to minus diffusivity concentration gradient. So, and also can be expressed like the concentration, mobility, and the driving force. The driving force for mass transport, as we mentioned before, is a negative chemical potential gradient. So here, based on this equation derived from the Fick's first law, we know what the intrinsic material property diffusivity can be well described how fast the atoms moves in solid materials. And also, you also can use the mobility to describe this intrinsic material property. The mobility defines as when you apply a unit driving force, how fast the atoms moves in your materials, right? And if there only exists one driving force, we call it as a chemical potential gradient. This gradient will drive or push the atoms moves from where? From the location with high chemical potential toward to the location with low chemical potential to minimize the free energy of the system. So this is what we call the mass transport process. But however, this is the case when there only exists one driving force, which we call the variation of the chemical potential, right? In space. But however, if there exists other driving force apply on your system, on your materials, how can we modify the atomic flux? And we also need to discuss does this driving force, how this driving force affect the atomic flux. So for example, like if you apply the electrical field temperature gradient on your materials, how these two driving forces affect the atomic flux? Does that affect a lot or just a tiny? Then we can ignore that. And we are going to talk about the capillarity and stress effect. These two driving forces actually, what's a capillarity? If your material is not a flat material, it's with a curve something, with different curvature exist on your materials, and we need to modify the chemical potential of the atom at the curve surface, right? And that will result in a variation of chemical potential. So in the space, there's definitely a chemical potential gradient exists, right? And if there are some crystal imperfection site, for example, like the dislocations, that will cause a localized stress field, right? This stress field also will affect the chemical potential of the atom, right? So, and based on this, like capillarity or stress effect, we need to modify the chemical potential of the atom. Then that will call, then as long as it be modified, so in the space, there's definitely a variation of the chemical potential gradient. So we need to calculate what's the magnitude and what's the direction of atomic flux Okay, so this is the outline for lecture 2. You need to calculate or well describe the magnitude and direction of atomic flux in your materials. So first of all, you need to identify your material system. Is that the ionic material or the metal materials? What kind of material we are talking about? Is a BCC, FCC, different structures, any dislocation, something? And the second part is a boundary condition. Boundary condition means that are there any other driving forces applied on this system? For example, did you apply a electrical field or temperature gradient on it? Does it have a curve geometry? Something like that is we call the boundary condition something. Okay, so for the first section, we are going to talk about is define what's the diffusion. Diffusion actually is a mass transport phenomenon in solid materials. And the driving force, as you know, is the chemical potential gradient instead of a concentration gradient, right? So it's a chemical potential gradient. So as long as you can formulate the chemical potential at each location, then you can understand are there any chemical potential exist, gradient or difference or variation exist in your materials. So you can determine will that mass transport happen in your system. And I also remark to explain why the driving force is not the concentration gradient, because as you know, the spinodal decomposition, this phenomenon actually the atoms moves from low concentration toward to high concentration. But if you use the energy point of view, the atoms is moved from high potential energy, high potential toward to low potential, also to minimize the free energy of a system. So the driving force for mass transport or diffusion in solid materials is a minus chemical potential gradient would be much suitable, serve as a driving force. So please use the energy point of view to describe the driving force in mass transport. And in the second section, we are going to talk about the electron migration. Based on this name, you know that electron migration. So it's an electrons flow cause the atomic migration. So based on this, you know the driving force should be, the boundary condition should be what? There's must an electric field apply on these materials, and that will cause the electrical potential gradient, or that will cause the current or electrons flow. And this electron flow or electric field probably will affect the mass transport. So we are going to talk this in section 2. And in this case, actually in these sections, we talk about two different kinds of material. The first one is the ionic materials, and the second one is the metal. And there will be the different cases, right? If you apply the electron field on ionic material, what happens? You will push the positive ion toward where? It's a positive, so must be toward to cathode, right? But however, if you apply the electrical field, a very large electrical field on metals, there'll be a different story, right? Because for metals, if you apply the large electrical field, that will cause large electrons flows. As long as this electrons flow is quite large to push the positive metal ions toward to anode. So under high current density, that means there's a high electrons flows high enough to drive or push the positive metal ions move toward to anode by the momentum exchange. And this phenomenon, people call it as electron migration. So as we mentioned, in this section, we are going to talk about two different materials, and all under the same condition. Is like we apply electron field on it and discuss the difference and how the atomic flux in these two different materials, the two different types of materials. And in the third sections, we are going to talk about the thermal migration. Based on the term thermal migration, that is exists a temperature gradient along these materials, right? So there's a temperature gradient or thermal potential gradient being applied on the system. So that will cause a heat flux. As long as this heat flux large enough, probably they will also affect the atomic flux, because as we know, like there's a coupling coefficient, right? Between the thermal driving force and the chemical potential gradient, right? Okay, and this then in the section 4, we are going to talk about the capillarity effect. Capillarity effect actually is when you these two different effects, actually you just modify the potential gradient. So actually it's for the capillarity effect happens when there's a curve solid materials, and because the atom at the convex side with higher chemical potential, and these atoms tend to move toward to convex side with a lower chemical potential to minimize the free energy of the system. So the driving force will be also is to minimize. It's a potential gradient, but the purpose is to minimize the free energy of a system. And the same thing happens on the stress field, stress migration, because in your material, in your crystal, less stress field exists in your materials, and that will cause the variation in chemical potential. So in order to minimize the free energy of a system, the atom is going to moves from compressive region toward to tensile region. Okay, so how to deal with this two or more driving force in the meantime, and how this driving force will affect the atomic flux. We are going to talk this in the following slides. And the hint will be something like if you think about, if you use the free energy point of view, you can have idea. No matter what kind of driving force apply on this system, as long as it causes the variation in potential energy and in the potential chemical potential or any potential energy. So based on the thermodynamics, this system definitely move to the direction to minimize the free energy of a system. So the driving force in atomic flux must be the minus potential gradient. So you just need to summation all the variation in potential, then take the gradient, minus gradient, then you can get the driving force. You can get the driving force, summarize or in the integral driving force to drive this atomic flux. Okay, so that I will give you some example. But before we move to these 4 driving forces, we need to define what's the diffusion in solid materials. So driving force the diffusion can be described as or be defined as atomic flux divided by minus concentration gradient. So which we call it as a diffusivity. We use the diffusivity to describe how fast the diffusing atoms moves through your materials. And also, some people will use, instead of diffusivity, some people will use the mobility to describe diffusion phenomena. And then we are going to talk about what's the diffusivity. We do have different diffusivities be defined based on different material system and different reference coordinate. Then you need to know here in this textbook, we talk about 3 different kinds of diffusivities based on different material system and reference coordinate. And then in this diffusivity, the first one is we call self-diffusivity, and intrinsic diffusivity and interdifusivity. And at the end of these sections, we are going to talk about what's the Kirkendall effect. This is a typical diffusion phenomena we can observe in diffusion couple. So we are going to talk about what's the Kirkendall effect. And the two characteristics for Kirkendall effect is void formation and the lattice plane shift. Okay, so let's move to the mass transport in solid materials. In order to well describe the mass transport, people use the atomic flux. So the mass flux or atomic flux actually can be equals to flux actually is the numbers of diffusing atoms per unit area and per unit time equals to concentration times the velocity of this moving atom. And based on fixed first law can be expressed like the concentration, mobility, and the driving force. So the mobility here be defined as you move here to a button, so is when you apply a unit driving force, which is chemical potential minus chemical potential gradient on this material, on these atoms, how fast this diffusing atoms moves. We call it as a mobility. So usually in mass transport system, you can use either the diffusivity or mobility to describe describe this material, or you can say diffusivity or mobility is the intrinsic material property of your interesting materials, especially in mass transport. So what's the relationship between the mobility and diffusivity? So we are using this slide to demonstrate the relationship between the mobility and diffusivity, because both of these can be an indicator to describe how fast the atoms moves through your materials. So based on the fixed first law, you know the atomic flux can be expressed like a negative diffusivity concentration gradient or concentration, mobility, and driving force. And as you know, what's the chemical potential gradients? chemical potential be defined as when you ended one atom A, how the change of the free system, right? So it can be expressed like a mu A0 is the chemical potential of atom A in pure A materials, and plus KT log XA. XA is atomic fraction of atom A. So based on this, I just grab this equation, and we just do, because actually we want to know the relationship between the chemical potential gradient and concentration gradient, right? But atomic fraction actually is some kind of concentration gradient, but I want to convert it to concentration gradient. So let's do this way. XA, atomic fraction of atom A in this alloy, can be expressed like a Ca, concentration times the average atomic valence in these materials. So we successfully to converted the atomic fraction to the concentration. So you got a relationship between the chemical potential and concentration. So why we can just do this kind of calculate? So if you what's the atomic fraction? So if you atomic fraction actually is the valence fraction. Valence of atom A in total materials, right? So sometimes what's the Ca? Ca is the number of atom A in our materials, right? So you divided by the total valence of your material system. Then times what? Then what's the average atomic valence? So it's the average atomic valence of atom A. So if times that this is the atomic valence A times the number of the atom will be the total numbers or total valence of the atom A, and divided by total valence. So it's the atomic fraction of atom A, right? So based on this, you use this mu A0 plus this term, you take the gradient operator on this equation. And for example, okay, so what's the atomic valence? Give you just a roughly idea is the order will be like 10 to minus 23 cm, cubic cm. Okay, so this is some idea about the average atomic valence. Okay, so we take the gradient operator on this equation, and the gradient is you take the gradient is partial to distance, right? But the chemical potential of atom A in pure A material, this is not varied with, not change with the distance. So just take a gradient, this will be drop this term out. And also this omega, the average atomic valence do not change with the distance. So you can drop this term out. So the rest of it will take the gradient operator on this. So you got the KT Ca reciprocal of Ca and gradient of Ca. So we got successfully get the relationship between the chemical potential gradient and the concentration gradient, right? So this results show you that as long as a concentration difference, you have a large concentration or large concentration gradient, usually the chemical potential gradient is large as well. It's a proportion relationship. Okay, so we substitute this chemical potential gradient with this concentration gradient. So we got a Ca Ma, and this term we substitute with this. So we got, and Ca is drop out, this turn out. So left we have KT Ma and concentration gradient. So when you compare this, you got what? The diversity can be equals diffusivity of this material equals to mobility times the K and T. So here you have some idea about what's the relationship between the mobility and diffusivity in your material. So is diffusivity and mobility is a proportional relationship, right? So you can use this no matter it's a mobility or diffusivity to describe the mass transport property of your interesting material, and this we call it the Nernst relationship. Okay. So next we are going to, now you have an idea what's the diffusivity and mobility, and they are the proportional relationship, and usually people use the diffusivity to describe the mass transport property of this material. So how to get this diffusivity? Based on the fixed first law, you can just measure the atomic flux divided by what? The minus concentration gradient. Then you got the diffusivity. Right? So next we are going to talk about based on different material systems and different reference coordinates, and we are going to talk about 3 different kinds or types of diffusivity. And diffusivity, as you know, is one of the intrinsic material properties, and you can use this diffusivity as an indicator to describe how fast diffusing atoms moves through your materials. So the first one we call a self-diffusivity. Star D is the diffusivity of component I in a chemically homogeneous medium. So this is the diffusivity. And the material system we are talking about is a chemically homogeneous medium. So what is a chemically homogeneous medium? That means within your materials, the concentration of the concentration of your interesting atoms is uniform along your materials. So there's no concentration variations exist in your materials. So it can be a pure materials, but also can be an alloy. For example, like if you have an AB alloy, as long as the concentration of component A is uniform along this sample, you still can consider this kind of material system. You also can use the self-diffusivity D star to describe the diffusivity or the diffusivity. You also can use the D star to describe in this kind of material systems. And some people probably will ask, yes, there's no concentration variation in space or along your materials. So what's the driving force here? And actually, the atoms always move around, right? Even there's no net flux, but still have the atoms always do the random walk. So the average displacement of the atoms can be considered equals to 0. So this kind of diffusivity, we call it as self-diffusivity. So it's definitely chemically homogeneous medium. But however, if we change the material system to chemically inhomogeneous medium, then that would be the diffusivity we are talking about would be the intrinsic diffusivity Di or the interdifusivity D, and this use this symbol to represent interdifusivity. And both this diffusivity we're talking about is happen in the chemically inhomogeneous medium. So what's a chemically inhomogeneous medium? It means that the concentration of your interesting atom is not uniform. There's a concentration variation along your interesting materials. So we call it as a chemically inhomogeneous medium. So both these cases just happen on the diversivity is measured in the chemically inhomogeneous medium. And the difference between these two diversivity is the observation reference, reference coordinate. If you observe the reference you choose is in a local frame. Some people call it as a crystal coordinate. Then the diversivity you derived will be the intrinsic diversivity. But however, if the reference coordinate you choose is in the lab coordinate, then we will call it the diversivity you derive or you measured will be the interdiversivity. So let's take a diffusion couple, AB couple, as an example. Now we have a chemically inhomogeneous medium because now you have this AB diffusion couple as your material system, and in space along these materials, yes, they do exist chemically inhomogeneous, right? Because the concentration of A is like probably is here, but we don't have any A in B region. And if you plot the concentration of B is like a 0 here, and it will present some concentration of atom B here. So let's do exist chemically inhomogeneous. And as we know, as long as you heat this diffusion couple to the high temperature, and this diffusion happens between A and B. So we assume at a high temperature, there's a flux J toward to right-handed side, and there will be a JB, the flux of atom B toward to left-handed side. So we assume the JA is larger than JB. So that means the more A atoms will move to right-handed side, so that will push the interface toward to left-handed side. So the interface is going to move to left-handed side with velocity v during the diffusion process. Okay, so now what's the intrinsic diversivity dI? That means if you stand on this interface and the flux you measure while you stand at this interface, the flux you measured divided by the minus concentration gradient, the diversivity. So the flux you measure when you stand on this interface and you divide it by minus concentration gradient, and the diversivity you derived will be, we call it intrinsic diversivity, D. Okay, so you can just simply divide that, so you can get the diversivity, and this diversivity is, we call it intrinsic diversivity. And for the interdiversivity, in this case, that means if you stand out of the system, stand in the lab, then you also calculate or measure the atomic flux through a specific interface, and you divide it by the minus concentration gradient, and the diversivity you get will be the interdiversivity. Okay, so this is the big difference. The major difference between the intrinsic diversivity and interdiversivity is based on different reference coordinate. And for the intrinsic diversivity, you stand on the crystal coordinate, and during the diffusion, you are going to move along with this interface, right? And for the interdiversivity, you stand out of the material system. So then you also will get the atomic flux. So this diversivity, you call it is an interdiversivity. Based on this, so far you know the interface is going to move to the left-handed side. So the other, actually, I also label the vacancy flux. So based on, if you take a look on the specific surface or interface, specific cross-section or specific interface of this system, the net flux, the summation of the net flux of different components should be equals to 0. So if JA will be larger than JB, so in order to reach the net flux equals to 0, so there must be a vacancy flux toward to left-handed side. Probably some people will ask about why the net flux need to equals to 0. If the net flux not equals to 0, that means under the per unit, under the certain time period, the atoms, because the more atoms is going to move to right-handed side and less atom move to left-handed side. So after like a couple years or something, like after a long time period, this material system is going to move, right? Because always there's more atoms move to right-handed side, less B atoms move to left-handed side. So that will cause your materials moves over time, but it's not going to happen, right? So if you the net flux at any specific plane should be equals to 0. So based on this, we can draw a vacancy flux to balance the atomic flux of A atoms. Okay, so we got the vacancy flux toward to left-handed side. Okay, so now you have some pictures about what's the self-diversivity is happen when your system is chemically homogeneous materials, and what's the intrinsic and interdiversivity. So I grabbed some figures from the internet and demonstrated that I hope you can have more idea about what's the intrinsic diversivity and interdiversivity. If for this case, we also have a AB diffusion couple, but in this case, the JB is larger than JA. So the JB is here. JB is larger than JA. So based on this, can you determine which direction of this interface moves? Would be JA is larger than JB. So let's move to left-handed side. So that is going to push this interface toward to right-handed side. So the interface is going to move to right-handed side with the velocity v, right? And based on the right? And sorry. And if the intrinsic diversivity, that means you stand at the interface, and the flux you measured and divided by the minus gradient, concentration gradient, and you got the intrinsic diffusivity. But if you stand out of the sample in the lab coordinate, then the atomic flux you measure and divided by the minus concentration gradient, the diffusivity, you call it as interdifusivity. Okay, so and based on this, can you determine, by the way, based on the net flux equals to 0, can you determine which direction of the vacancy flux goes to which directions? Because JB is larger than JA, so there must be a vacancy flux toward to the right-handed side to balance the flux of atom B, right? Okay.